There we go. The computer has life. Let's get started. All right, so a couple things. Number one, sign-in sheet is being passed around as we speak. If you did not get copies of homework 7, the column and frames homework, I've got that up here. I've got that due Friday the 14th. In all honesty, you could finish it now, but with reinforced concrete having an exam on Wednesday, I thought it'd be nice and have it due Friday, so that way you're not having too much all at once. I figure that's fair, right? You are quite welcome. And in addition, I've produced that table that you see there on the slide. That table is our agenda from here out, okay? So that's the agenda for the rest of the semester. So you all have homework now is due on the 14th. On the 14th, I might even give it to you on the 12th, but I'm going to give you homework 8, which is on continuously braced beams. I'm going to have that due the 21st, and then discretely braced homework is going to be due on the 28th, okay? So from here on out, every Friday, I have an assignment coming in, okay? All right, so everybody okay with that? Now, every Friday an assignment will be due from here on out because, I mean, we don't have any exams between now and the end of the semester, but the trade-off is we got a little bit of homework, okay? Now, one other thing I will point out, because I am a nice guy and I will hold myself to my own schedule, if you look at the syllabus says on April 26th we have a makeup day, okay? Now, I know we're supposed to get some snow today, but I don't think we're going to have any cancellations. So here's what I'll do. It says makeup day, and assuming we don't have any major scheduling snafus, we will still have that makeup day. All right. Now, the trade-off is, at the very least, I may post a video on the playlist, just some, final tips, let's say, for homework 9. But assuming everything goes well, we won't have lecture. Okay. But I will post a video, and that video, I mean, depending upon where we're at, I'll post a video to make up for everything. In other words, one topic that we may not have time to cover at the very end is shear. But shear, like in concrete design, was a really big deal. And in steel design, it's not. Okay, it just really isn't. You need to check it, but it's incredibly simple, and 99 times out of 100, you never need to worry about it. You're never changing beam designs because of shear. But we'll get to that as we progress throughout the semester. In terms of topics, from here on out, it's beams. Okay? That's what we're talking about for the rest of the semester. It's beams. So, everybody good? Does anybody have any questions on homework 7? Because I know you all are almost done with it, right? Oh, so you've had plenty of time. I can just feel the sarcasm. I can feel it. All right. Okay. Now, today, you get to see my best slide ever. My best slide ever. What's that? No, it's better. Better. Okay. So you're going to see it in your handouts. You're going to go, what's going on with this? And then you'll understand why. Okay, so we're beginning our discussion on beams. And I want to just go over bending in general and also talk about a very important parameter related to bending, which is ZX, the plastic section modulus. To start out, let's just sort of take it one step at a time. So the big difference between tension members and compression members is that members in compression like to do this thing called buckling. Okay, tension members really didn't. That wasn't an issue, so we never really were concerned about the stability of a tension member, but we were with columns. Well, with beams, it's really no different. I mean, with beams, you have a portion of the beam's cross-section that's in compression, the top's in compression, bottom's in tension, so a beam is going to want to buckle as well. Okay? Now, the way a beam buckles, or its buckling capacity, is a function of how far apart your braces are. Now, your braces could mean a number of things. They could mean cross frames. They could mean other beams tying in, the floor system itself. We'll get into that. But we will create a term throughout this this discussion called the unbraced length, and we'll call that L sub B. And an L sub B is related a lot like a column's slenderness. In other words, the longer LB is, the longer the space between braces in a beam, the weaker that beam is, okay? Because it gets more slender and it wants to buckle. However, because of the mechanics associated with beams, a beam may reach its full capacity before the beam buckling happens. Now, its full capacity takes a little bit of discussion. It's not as simple, well, actually it is simpler mathematically than what you did in Engineering 216 when you did, or when you took mechanics of deformable bodies. It's actually a little easier than the yield moment and whatnot. And I know everybody in here is an expert in mechanics of deformable bodies, right? You all love that stuff. But I will do my diligence and do a quick review, if you will, of some of the stuff that's relevant in Engineering 216, just to sort of bring everybody back up to speed. So beams, I mean, it's one of those things where, you know, if you graduate with an engineering degree, the one thing that I would want you to understand, like if you ask me, just any student graduating from a civil engineering degree or a mechanical engineering degree, if there's one topic that I want a student to understand, beams, just period, you know. Shear and moment diagrams, beam analysis, beam design, deflection, beams, period, you know, in a nutshell. It's the one thing I want students to be able to understand because they're just so fundamental, okay? Just about any system that you are designing that has forces on it, whether it's a building, a bridge, an airplane, a car, any system that you are designing has some pieces in it, or the system itself is being bent in some fashion or another. There's something in that system that's probably being bent, okay? So because something's being bent, you have to understand how to handle bending stresses, okay? Now, beams experience shears and moments, so they would develop shear stresses and bending stresses. You all in concrete design, we handle each of those independently, and we're going to kind of do the same thing in here. I mean, we did bending moments first, and then we tackled shear. Sort of going to be the same thing in here, although the shear discussion that we have in here is going to be very, very short because there's not really a whole lot to say about it. So let's go back to fundamentals. So I have a beam, samurai sword, or lightsaber, or cake cutter, you know, through the beam. If I'm treating this as if it's a two-dimensional system, then there are at most 3 unknown resultants inside the beam. Some unknown axial force, some unknown shear, and some unknown moment. And so those 3 components, those 3 unknown resultants, I essentially solve for those using the 3 equations of equilibrium, right? Sum of forces in the x direction, sum of forces in the y direction, sum of moments. 3 equations, 3 unknowns. That's structural analysis in a nutshell. Now, as we'll see in a moment, I even put no pun intended on the slide. That'll get a couple likes on the video right there. Yeah.
Maybe subscribe.
Maybe hit that subscribe button. You know. As we'll see, okay, you generate 3 forces. Now, axial forces. Now, let's just go back to mechanics. Axial forces generate normal stresses. You know, sigma equals P over A. I've got to believe you remember that. You know, I take a bar and I yank on it with some force P. Has some cross-sectional area A. The stress is P over A. I mean, we did that in here. You know, so you should remember that. Now, bending moments and shear forces generate normal stresses and shear stresses. Now, the shear stress, I'm going to worry about that later, but right now I want to focus on that bending moment, okay? Now, in order to make these derivations, we're going to make some basic assumptions. So one of them is linear behavior. We're going to assume that the beam is behaving linearly. Now, the stress and the strain are proportional to one another, okay? Now, another assumption we're going to make is strain compatibility, which if you haven't had concrete design in a while, it might have been a while since you've seen this, but if you're in it now, we've used this not too long ago. I mean, remember how we use similar triangles to say, well, if we've got the strain at the top of the beam, we use similar triangles to get the strain in the steel or the strain in other layers. So we assumed that the strain was linear, right? That's essentially the same thing we're talking about here when we say strain compatibility. that the strain profile is linear. So essentially, if you have a linear strain profile and you have linear elastic behavior in your material, then the stress should be linear. Make sense? You know, so just taking strain and multiplying it times a constant. In this case, that constant is Young's modulus. We're also going to consider small deflections or first-order behavior. Remember that example of the guy with the backpack or me with the backpack, and Caleb doesn't like me very much, so he pushes me, and it makes me want to fall more than if I didn't. So we're going to assume for now that first-order behavior is what governs. So if you use these assumptions, all right, we can treat the problem as follows. Okay, so we have a beam that's being subjected to some loads or what have you, doesn't really matter. Okay, now the beam has some arbitrary cross-section. So if I samurai sword, lightsaber, or cake cutter through the section and look, it could look like anything. It doesn't really matter what it looks like. So I've got what the solid mechanics refer to affectionately as the stress potato. It's a term. It's a term. So it's just some arbitrary cross-section. Now notice how I've got that blue line going through what I'm calling the centroid of that cross-section. Okay. Now we can use statics or structural analysis to determine the axial force in the moment. Now we also know that those forces generate stress. The question is how much. Well, if we've got two unknowns, and we're assuming everything's linear, I propose that the stress profile along that depth should be linear in nature. Now, the equation of a line is y equals mx plus b, or some constant plus some other constant times y. Okay, and again, this blue dashed line is going through the centroid. The point is to try and define that stress profile. Sound good? I'm bringing it back to basics here. Okay. So we've got this line. It seems to make sense based on all the assumptions that we've made, but we've got these constants. Okay. We've got two known forces. We've got two unknown constants, two equations, two unknowns. We should be able to go to work. Okay. So how does this work? Well, essentially, you would go through and integrate your stress profile, go through and plug and chug, and it's not so bad when you go through and chug it out. You end up getting that your first constant is P over A, which is normal axial stress, which is, I believe, what everybody is fairly familiar with at this point. And then your second constant is M over Ix. Remember, Ix is your moment of inertia. So your stress profile is P over A plus My over I. And I have got to believe that everybody remembers sigma equals My over I. That is fundamental from mechanics. Sound good? So if I've got axial forces, bending moment, shears, what I'm saying is that your normal stress in that beam is P over A plus My over I. And if you don't have any axial force on the beam at all, it's just My over I. So My over I is your fundamental axial stress equation, your axial stress equation for a section subjected to bending. It is a function of the bending moment applied, the moment of inertia, and the distance y that is measured from the centroid. Remember, our blue dashed line was going through the centroid, so that's where bending stress is 0. Okay? Make sense? Sometimes y is called the neutral axis, because everything, let's say, on one side of the axis is in compression, everything on the other side of the axis is tension. Right there is where there is no stress or no strain. Yes?
Blue dash line on the potato wasn't
It's kind of through its centroid.
but it wasn't there's not you said 0 stress at the blue dash line, but the potato is not.
Okay, that's a good question. The reason why is because of the presence of P. Okay? So this right here, see that? Okay? This is a blown up version of the total stress. And I'm saying that the total stress equals P over A plus this. Okay? In other words, if I take that beam and I just apply an axial load to it, it doesn't matter where the centroid is. I'm going to get stress right there, and it's just P over A. If, however, there is no axial load, then this term goes to 0. Okay? I'm saying that the magnitude right there is P over A. So with no P, this stress profile turns into that. That's a good observation. That's a great observation. Does everybody else understand that? Everybody good? That's a good observation. Okay. Now, if I have a beam that's not a stress potato or an arbitrary cross-section, if I have a beam that has that's symmetric, let's say like an I-beam, then then the actual middle of that beam, half the height, that's where the centroid is. So the maximum bending stress is going to be either at the top or at the bottom. It's going to be the same value, just different signs. One's going to be in compression, one's going to be in tension. Sound good? Okay. So in order to determine that, I'm using sigma equals my over I, and my y distance is d over 2, or half that depth. Sound good? Okay. Now, if I do some manipulating, take this and rearrange my fraction a little bit, I have m divided by the following quantity, the moment of inertia divided by half the depth. For symmetric I-beams, for doubly symmetric I-beams, that has a very special name. We call it the section modulus. We call it S sub x. Everybody turn to table 1-1. I want you all to see this on the manual. Just any I-beam. It doesn't matter. Everybody see that? You should have that tabbed, right? The W sections. All right? Now go to axis XX or axis YY. It doesn't really matter. And you should, for each of the axes, you should have 4 properties, right? You have a moment of inertia, I, right? You have a section modulus, S, which if you want to calculate S for a given beam, just take that and divide it by half the depth. It'll work. Now, you have a radius of gyration, right? Everybody recognizes that, but what's the other one? Z. What is Z? We're going to get to that today. All right? Sound good? What's that? Yeah, it is. See, there's a Z right there.
I didn't say that.
Oh, I thought you did. I'm sorry. I'm sorry. There's no Z.
Us in the picture.
There. We'll get to that here in a second. We're actually going to get to that picture very soon. Now, one thing I want to point out, okay, the reason why we have just a single section modulus is because this distance and this distance are the same, okay? Now, why are they the same? The reason they're the same is because the section is symmetric, okay? Well, what if this top flange was smaller than this bottom flange? What if that happened? Is that a common instance? Well, in bridges, you better believe it's a common instance, because in bridges, you are tailoring the size of your girder to meet the specific load demands. It's very common that you have different size flanges on the top and bottom. And because of that, your central is not going to be smack dab in the middle. It might be shifted up or down some. So from a notation standpoint, you might have a section modulus, let's say, to the compression flange and section modulus to the tension flange. I just want everybody to be aware of that notation. What's that? Oh, that's mistake 6.5. Oh, 6.5. Maybe 6 3/4. All right, so let me make a note of that. I can't change it on here because I don't have the math type software. But yes. I heard that. Whoops. Oh well. Okay, but I got it right on the bottom, so I don't. That's why I'm calling it 6.5, because this is XT and XT. So yeah. What? Oh goodness, you're expecting too much out of me. All right, everybody okay with this? Okay. Now, so is everybody in agreement that in elastic behavior, the bending stresses look something like this? Everybody in agreement with that? So where are the largest stresses? Top and bottom, right? So if I limited the stress up here to, let's say, the yield stress, seems like a pretty reasonable limit, I can say, all right, let's set that stress equal to Fy and solve for the moment, and I would then compute what's called the yield moment. of that section, right? So the yield moment would be the section modulus yield stress. Everybody okay with that? Okay. Now, all right, okay, so first off, just on a notation standpoint, if the section was singly symmetric, we would not have just a yield moment. We'd have a yield moment for the compression flange and a yield moment for the tension flange, and when we do our calcs, we just take the lowest. Everybody okay with that? Okay. Now, let me ask you this. Is the yield moment the ultimate capacity of a beam? And I'm saying the answer to that question is no. No. Okay, with an exclamation point. I should have put a triple exclamation point. Okay? Steel beams can withstand bending moments far larger than their yield moment. Okay? Now, that's only true under certain conditions, specifically if they're braced well enough, and we'll get into that. But I want everybody to be clear that beams can withstand moments far larger than their yield moment. Okay. Here's my best slide. Okay, now if you look at it in the handout, it looks a little weird. There's a reason why it looks a little weird. Okay, all right. So let's say we have a steel beam, okay? Now we apply some moment. Now here on the right, I've got the bending stress profile. So let's take that beam and let's start to bend it. Now what happens at the very beginning is the bending stress profile does something about like that, okay? It behaves linearly until right there, okay? And it behaves linearly until the top and the bottom reach a point called Fy, okay? So at that point, the beam has behaved elastically, and we've reached the yield moment at the top, okay? Now we call that the yield moment, okay? When the top and the bottom reach Fy. Sound good? Now, my question to you is, what happens if we keep applying moment? Like, what if we just kept bending it? Well, let's see what. Well, we're going to do it, but let me ask you this: would you agree that the beam has yielded right at the tippy top and the way down at the bottom? We've reached yielding here and here. What about, let's say, right there? Have we reached yielding there? This can do just fine, right? Same thing here and here and here. The middle part of the beam is just fine. So what I'm saying is, here's the beam at the yield moment, but if we keep increasing the moment, it's going to do that, okay? That yielding is going to penetrate throughout the section until we've yielded the whole thing, okay? That is the ultimate capacity of the beam, and we call that the plastic moment, okay? Oh, wow. That's my best slide. Downhill from here. I think the mistake counter ought to be dialed back to 4.2 just for that, so that's just me. Everybody okay with that? Does that make sense? Okay, there's that. I'm okay with showing you this one again. All right, so here we go. All right, so what happens if we kept increasing the moment? Well, I had that there. I should have had the soundtrack throughout the whole thing, you know. All right. Maybe I should have had the. Anybody remember the Price is Right? Remember the yodeler music? As it's yielding. Yeah.
They don't do that when we do model, do they?
I don't know.
I don't think they do.
I don't know. I'm behind on my Price is Right. I just remember Plinko. That's all I remember. All right. So going back to steel design, what I'm saying is that the plastic moment is really the largest moment that a steel beam can take. In other words, if there was a beam right above me and it was loaded up till the yield moment, I'd be perfectly fine with taking a nap under that beam. Okay. But if the beam was experiencing its plastic moment, I'm out of there. Okay. Because what's happening is this is when the entire cross-section has yielded, so the entire cross-section is free to deform. If you have a point in a beam that has reached its plastic moment, in the world of structural engineering, we say that it has developed a plastic hinge at that point. And it sort of behaves like a hinge because it sort of freely rotates, right? If it can't resist moment, I mean, instructional analysis, what was a point on a beam that could not resist moment? What do we call that point? A hinge. So, pin, hinge, it's the same thing. All right. We need a means of computing this value. Okay. Now I'm going to spit out a new term to you. Okay. Now the elastic neutral axis, and I'm calling the elastic neutral axis just to differentiate. But the elastic neutral axis of a cross-section is where the centroid is, which everybody, I think, in this room knows how to compute the centroid. Sum of AY over sum of A. The plastic neutral axis is where the compressive forces equal the tensile forces. Now, that's got to be true no matter what, but we're going to be able to relate this to what's going on in MP. Now, aren't these the same thing? I mean, doesn't the centroid and where the area or the compressive forces equal the tensile forces, isn't that the same thing? Not necessarily, okay? Because of the symmetry, it might be there and it might not. In other words, if I have a doubly symmetric cross-section, like a wide fan shape, okay, like a W10 by 49, and I compute the centroid and the plastic neutral axis, they're in the same spot. In other words, here's where the centroid is, and then if I look over here, everything in compression equals everything in tension, so it's the same spot. But if I make that a singly symmetric cross-section, the elastic neutral axis and the plastic neutral axis are not necessarily in the same spot. Because once I start yielding throughout the cross-section, what ends up happening is that plastic neutral axis, it starts to shift, and it's got to shift to maintain the fact that compression equals tension. And at MP, they might be in different spots, okay? So that's something to be aware of, okay? If you go to the angle properties, this is listed straight in the spec. You remember when we were doing tension members and I said don't use the X sub P and the Y sub P's? Remember that? Here's why. The Y bar and the X bar are where the centroid are. But this Y sub P and X sub P, that's where the plastic neutral axis is. Not necessarily in the same spot. Okay? Make sense? So, just food for thought.
Plastic neutral axis change?
What's that?
Why is it change?
Because as you start yielding throughout the cross-section, it's got to move in order to maintain the fact that compression's got to equal tension. And the only way for equilibrium to be maintained is for that axis, the point where compression gets split up into tension, it's got to move. It's just physics. And if you're having a hard time going, well, wait, is that always the case? Or we have an example where we're going to look at that. It stays the same, yes. If it's symmetric, if it's something like a W shape, if it's a channel being bent about that axis, any time where it's symmetric about that axis, you've got no issues. But if it changes, if you've got something like this where the top flange is a different size than the bottom flange, they won't be in the same spot. And I'll be able to prove that to you here in a little bit. Sound good? So just bear with me. We'll see how this works out. Okay. Now, all right, so let's talk about this. So once we determine where the P and A is, we can do this by summing moments. Okay. Now, the plastic neutral axis is essentially where the forces in compression equal the forces in tension. Now, this should not be an off-the-wall calc for you all because we've been doing this in concrete design all semester. Right? What are your compressive forces? 0.85 FC prime AB, and then your tensile forces are ASFY, and then you determine what is that A distance such that C equals T, right? Now, we had to deal with forces and stresses in concrete design because we were dealing with a composite beam. We had concrete and we had steel. We had two materials. Here we don't. Everything is the same material. And usually, in most cases, everything is the same yield stress. In other words, we've got 50 KSI steel, let's say, across the board. So it actually becomes a little easier because instead of trying to find the location where the forces up top equal the forces below, we could say, let's just find the point where the area above equals the area below. In other words, whenever this area above equals this area below, we're good. That's where our plastic neutral axis is. Okay? Now, in order to determine our plastic moment, what do? We sum moments. I mean, how did we do the concrete beam analysis? We said a force times a distance, right? Make sense? All right. Well, if I look at, let's say, this diagram, I'm proposing that the plastic moment is this compressive force times its moment arm plus this tensile force times its moment arm. Pretty much the same thing we did in concrete design. Now, because it's steel and because it's the same yield stress, I can factor the yield stress out. So if I look at my equation here, I've got compressive force times moment arm plus tensile force times moment arm. I factor out the Fy, and all I've got is area times moment arm plus area times moment arm. That term inside that set of parentheses is a section property. I'm calling that section property the plastic section modulus, Zx. Okay? Does that make sense? Everybody okay with this so far? Now, Zx, I want to be clear, is only meaningful if the beam is made of a single material. Okay? In other words, if I'm using all 50 KSI throughout, we call that a homogeneous beam. Any time that we're using the same material across the board, Zx becomes meaningful. There are it is a very real possibility that you're doing, let's say, a highway bridge design, and you use, let's say, 50 KSI steel for the top flange and for the web, but for the bottom flange, you use 70 KSI steel. That's very possible, okay? And in that realm, Zx really wouldn't have much meaning because Zx is a geometric property of the shape. And since the shape has different yield stresses, it really doesn't help you very much. That type of beam where you have different grades of steel and different components, we call that a hybrid section. So if you ever hear me talk about hybrid girders, that's what I mean. Sound good? All right. So here's an example. Okay, so I have a beam and it's got different plate sizes across the board, and I want to determine Zx, and I want to determine the plastic moment. So I got a 12-inch by 1.5 inch top flange. I got a web that's 18 inches by 1 1/4, and the bottom flange is 16 by 1.75. Everybody good? Okay. Excuse me. Of course, the computer is taking its time. So. Any good jokes? How about them? Are you a fan? Is that what it is? For today. What's that? Yeah. So what, example 19? Okay. All right, so here's what I'm going to do. Okay, so here's our beam. Here's our beam. Okay? Now, what I'm trying to do is I'm trying to find this magic line where the area above equals the area below, okay? So here's how I'm going to do this, okay? Let's start off by labeling some things. So this was what, 12 times 1.5. This is 16 times 1.75. And this shape is 18 times 1.25. Sound good? All right, now, I'm going to take a wild guess and say that the plastic neutral axis probably falls somewhere inside this web. So we'll say that that is the plastic neutral axis. Sound good? Now, How far is that distance? We don't know, right? When you don't know something in mathematics, what do you tend to call it? X. So this is X. Now, if that is X, what is this distance? 18 minus X. Not too bad, right? Simple stuff. Now, if compression equals tension, we can handle this pretty easily. In other words, all the area above has to equal all the area below. So let's take care of the area above. If I wanted to write an expression for the area above that line, what would it be? All right, 12 times 1.5. And for the sake of brevity, I'm just going to leave the units off since everything is all in inches. So, okay, so 12 times 1.5 plus there we go. Equals what? So what about the bottom? Plus not bad, right? Sound good? So let's deal with the left. So 12 times 1.5 is what? All right, hold on. I can do better than that. Plus, okay, so we got to FOIL or distribute that multiplication. So we got 18 times 1.25 and 1.25 times x. So what is that? So what's 18 times 1.25? Say it again. Did you just go Casio FX 115 ES Plus? Is that what you just did? And what's 16 plus 1 point, or times 1.75? 28. So here's what I'll do. All right, I'll say let's subtract 28 from both sides. So subtract 28, and then let's add 1.25x. So over here on the right side, 1.25x and 1.25x makes 2.5x. The 28's cancel. And on the left, I have 18 plus 22.5 minus 28, which is, what'd you say, Mr. Crookshanks? There you go. Casio FX 115 ES Plus, right? What's that? It's like that lateral test when it was just there, man. All right. Okay. Now to determine ZX is really simple. You literally just take each shape one at a time. So what I'm going to say is we've got 1, 2, 3, 4, each flange, and then the web above and below our plastic neutral axis, and just some moments and add it up. So let's just start at the top, work our way down. So the area is 12 times 1.5. Now, what is the moment arm from the plastic neutral axis to the center of that flange? 13.75. So I'm going to say it's 13 plus 1.5 over 2. Does everybody see that? So you start here, you go up 18 minus 5, and then go up another half a thickness. Sound good? All right, next one. So we've got this upper portion of the web. So what's that upper portion of the web? Well, it's, what, 13, 1.25. Now somebody else, what's the moment arm? Somebody else. Huh? It's 13 over 2. It's 2.5 for the bottom one. Does that make sense? Okay. Now the bottom one, the shape below. So what's the area? Well, it's 5 times 1.25, and it's 5 over 2. Plus, then what do we have? 16, 1.75 times what? You tell me what to write. There you go. Okay. Now, I usually think it's easier. If you all want to do each individual calculation, that's fine, or somebody tell me what the whole thing is. I mean, it doesn't matter to me as long as we've got seconds. Nice try. Come on, Mr. Cruikshanks. Oh. Oh. I'll do that when I start signing homeworks. It's got some miles on it, right? Okay, so we have 533.25. Do we have a second on that? All right, well, let's take them one at a time. What do we got for this one? What's that? Okay, all right. Okay, guys, let's just do it one at a time. So the first one, I got 247.5. What's the second one? Anybody? What's that? 533.25. Okay, all right. So everybody is aware, this one was 105.625. This one is 15.625. And this one is 164.5. See, I had it here, so I had them all written down. Now, the units are cubic inches because you're taking an area and multiplying it times a distance. And since everything is in inches, that's where we get the cubic inches. So in order to compute the plastic moment, okay, we would say Fy times Zx. So it would just be, let's say, 50 KSI times 533.25 cubic inches. So what units is that going to come out to be in? Like, what are the units? It's a moment. Inch kips, right? So let's convert that to foot kips. So what do we get? What's that? Bless you. All right. Not bad, right? Sound good? Straightforward, right? Any questions for this? We got a lot more to cover. Am I good to just do a couple slides before we leave? I can't hold on. I can't hold on for one moment. We got too many moments as it is. Now that one, that's a good one. It could probably have been worded a little better, but that was good. All right, good? All right. So if you understand that, then computing capacity is pretty straightforward if you're not considering stability. Everything that we just did assumes that the beam will not buckle, okay? And so for our first instance of design with beams, let's just say, we are going to assume that beam buckling is not an issue. Then we're going to go back and say, well, what if you had to consider beam buckling? How would you do it? Okay? Now, in order to frame our discussion and make sure that we're talking about the same thing, now, I didn't even notice that one. That one was pretty good. All right. We need to discuss lateral bracing. We need to discuss the unbraced length of a beam. Now, L sub B, I want everybody to be clear on this. This is very important. L sub B is not how long a beam is. L sub B is the distance between braces. You could have a 40-foot long beam that's braced every 10 feet. Okay? So I want everybody to be clear on that. L sub B is the distance between braces. Okay? We call that the unbraced length. It is possible that a beam has an unbraced length of 0. For instance, if you have a situation like this where you have a beam and you've got, let's say, shear studs cast into the concrete deck, that deck is fully preventing that compression flange, that top flange, from buckling. It can't move at all because the shear studs are fully locking up with the concrete. So in this instance, L sub B would be 0. Okay? That's point one. An example of lateral bracing could be other beams framing in. So for instance, if I've got a floor system, I might have, let's say, a 30-foot long girder, but its unbraced length might be only 10 feet because from here, 10 feet, there's a brace. 10 feet, there's another brace. Okay? Those beams framing in act as braces. Okay? Does that make sense? Everybody okay with that? Didn't like braces? Neither did I. I feel you there. All right. Does that make sense, though? Okay. Another instance of a lateral brace is a cross frame, very common in bridge applications. So, for instance, this element is probably, a couple, 100, 200 feet long, something like that, depending upon the scale. But the unbraced length of this element is however far apart the cross frames are. Does that make sense? Everybody okay with this? For our first elements of design, when it talks about beams, we're going to assume LB equals 0, and that buckling is not an issue. We will then handle beam buckling later. Okay? So we're going to take it one step at a time, to sort of ease into it. Sound good? That's all I've got for you. For you folks not in concrete, we'll see you next week. For you folks in concrete, you're not going anywhere. So, well, you can if you want. All right, everybody have a good weekend.